Hello and welcome to another geometry lesson by eMath Instruction. My name is Kirk Weiler and today we'll be doing Unit 6, Lesson 2 on special quadrilaterals. So in our first lesson on quadrilaterals, we just sort of looked at quadrilaterals, the fact that they have four sides, the fact that their interior angles sum to 360 degrees, and we played around with them a little bit in the coordinate plane. Today we're going to talk about how many of the quadrilaterals fall into special categories. So let's jump right into that. All right, the special quadrilaterals. There are many special types of quadrilaterals. They are special because of sides being either parallel, perpendicular, or the same length. All right, now, you've had a lot of experience with special quadrilaterals. You've even been looking at them literally since before you could probably even speak, right? When you're your parents would open up a book of shapes and they'd point to a shape and they'd say, that's a blank and that's a blank, etc. So let's take a look at exercise number 1. Name as many special types of quadrilaterals that you can remember from previous courses. If possible, sketch a picture of each that you can remember. All right, so what I'd like you to do is actually pause the video now and sketch pictures of different types of special four-sided figures that you can remember, as many as you can, and try to write down their names. Take a little bit to do that now. All right, well, there's many of them, right? And of course, one that you might draw right away, both the simplest and maybe the most complex of them all, is a square, right? And again, we'll talk about what the technical definitions of all of these are and why I can't draw them very well as we go through this unit. But you've got a square, and of course, you've got something that is very similar to a square, right? Which is a rectangle. All right. You've also got, let's say, maybe a rectangle that seems to be shoved a little bit from one side, so a parallelogram. That's a good one. You've got maybe, let's say, one that's got a couple parallel sides, but not two pairs of parallel sides. That we might call a trapezoid. Let's see. Oh, one that you probably didn't think of, but we've looked at before, which is kind of cool, is something called a kite, right? So there's lots and lots of different types of special quadrilaterals, all right? And there's more than even what I put up here. If you had something called a rhombus drawn down, that's awesome. If you drew something and called it a diamond, that may have been what we were referring to as a rhombus. That would also be fine. There's lots of different types of special quadrilaterals. So let's play around with some of those types. Let's first begin with the trapezoid. All special quadrilaterals have specific properties that define the figure. We start with one of the broadest categories, okay, meaning that it includes lots of different subcategories, and that's what are called the trapezoids. So let's look at the technical definition of a trapezoid. Any quadrilateral that has at least one pair of parallel sides, meaning that they could have one or two pairs. Now, just want to put a little nod to a controversy here, okay? 20 years ago, if you were sitting in a geometry class and somebody put up the definition of a trapezoid, they would say a trapezoid is a four-sided figure with exactly one pair of parallel sides, meaning that you had one pair of sides that was parallel and the other pair of sides was not parallel. That definition changed a little bit, which shows that change can occur even in math, all right? So now, the way that the trapezoid is defined through what are known as the common core state standards is that it's a quadrilateral that has at least one pair of parallel sides, which means it could have one pair, but it could also have two pairs of parallel sides. It can't have three pairs of parallel sides because ultimately speaking, in a four-sided figure, you got two sides that are either opposite of each other or adjacent to each other, and therefore you can only have two pairs of parallel sides. Anyhow, there are some states still where math teachers continue to teach the idea that a trapezoid has only one pair of parallel sides. And I'm not trying to step on their toes at all here. This is just the way that the Common Core State Standards define a trapezoid. And so any state that has standards based on those standards this is how they'll define a trapezoid. All right, got that all out of the way, so no angry emails from math teachers saying, hey, you've defined a trapezoid wrong. It's not my fault. Look at the Common Core state standards, you'll see. All right, exercise number 2. State whether each figure below appears to fit the definition of a trapezoid. If it does, indicate the pairs of parallel sides using the standard arrow convention. All right, now remember, a trapezoid is any figure with at least one pair of parallel sides, means it could have one or it could have two. Okay, so letter A, right? Quadrilateral EFGH. It appears in this figure that EF is parallel to HG, and we show that by using little arrows. That's what I meant by the arrow convention. And we kind of looked at this once before when we were talking about figures that had parallel sides. So this is yes, all right? Yes, it appears that EF is parallel to HG. Now again, I'm saying appears because maybe they aren't parallel, maybe they're slightly bent inwards and they would eventually intersect. That's not the point of what we're doing right now. Now on the other hand, letter B, right, it may appear that WZ and XY are parallel, except it's pretty clearly obvious that this and this are different lengths, and so these are actually kind of getting closer together. This is also true that these two sides are getting closer together, so this is actually not a trapezoid. It is what's known as a kite, but we'll talk more about kites at a different point in time. Now, letter C, right, yet again, it appears that side QT is parallel to side RS. So yes, QT is parallel to RS. Okay. Let's take a look at D, E, and F. What I'd like you to do right now is pause the video, tell me whether or not it appears to be a trapezoid or not, and then mark parallel sides and state their names if you have parallel sides occurring. All right, well here in ABCD, we have our first instance of having a figure that has two pairs of parallel sides. It appears that side AB is parallel to side DC, and side AD is parallel to side BC. Notice how I put two arrow marks on that to distinguish this pair of parallel sides with that pair. So again, the answer here is yes, with AB parallel to CD and with AD parallel to BC. All right. Letter E was the most generic quadrilateral I could possibly draw. None of the sides appear parallel to one another, so that is not a trapezoid. And finally, letter F, that appears to be a square. But again, there's nothing wrong with a square also being a trapezoid. And here it appears that MA is parallel to HT, and MH is parallel to AT. So here we're going to say yes, that is a trapezoid with MA parallel to HT and MH parallel to AT. All right. Now, again, one thing that you're going to see time and again in this particular unit especially is that a figure that fits into one very broad category then might fit into another category, more narrow, and another category more narrow than that, all right? So this particular figure, which is a square, also happens to be a trapezoid. It fits within the trapezoid category. This particular figure is a parallelogram, and it also fits within the trapezoid category. So let's talk about parallelograms. Some of the trapezoids we saw in the last exercise had one pair of parallel sides, and some had two pairs. The ones with two pairs we call parallelograms. And even though the trapezoids are the most broad category, the parallelograms are the most important category. So let's talk about those a bit. Parallelograms. Any quadrilateral that has exactly two pairs of parallel sides. Exactly two pairs of parallel sides. All right. So exercise number 3. Quadrilateral ABCD below is a parallelogram. Letter A, state the parallel side pairs and mark them on the diagram. All right, well, why don't you go ahead and pause the video now. This is just what we did in exercise 2, except now I'm saying there's two pairs of parallel sides. All right, so simple enough, right? AB is parallel to CD. Whoops, and let's try that a little bit better. AD is parallel to BC. So AB is parallel to CD or DC, whichever, and AD is parallel to BC. All right, now sometimes people will say parallelograms have two pairs of opposite parallel sides. But quite frankly, two sides of any four-sided figure are either opposite or adjacent, all right? If they're adjacent, they intersect by default. So like AD is adjacent to AB because they're right next to each other. So there's no way, right, for two adjacent sides to be parallel because by default they intersect, all right? The only way for two sides to be parallel in a quadrilateral is for them to be opposite of each other. In other words, right across from each other. Anyway, let's take a look at letter B. List all angle pairs that must be supplementary based on A. Supplementary. They have to add up to 180 degrees. Well, keep in mind, right, that anytime we've got two parallel lines crossed by a transversal, right, two parallel lines crossed by a transversal, the same side interior angles, this angle and this angle, will always add up to 180 degrees. The same side interior angles will add up to 180 degrees. So if I were to just sort of like draw this in like this and kind of extend it like that, right, just so you can really see the parallel lines, then that angle and that angle must be supplementary, right? That angle and that angle must be supplementary, that one and that one must be supplementary, and this one must be supplementary. So I don't want to call them congruent because they're not, they add up to 180 degrees, but angle A and angle B and angle C and angle D and angle D and angle A, right? And really, you could summarize this by saying that two adjacent angles in a parallelogram will always be supplementary, right? So if this were 60 degrees, angle D, then angle A would be 120 degrees, right? Or if this was 30 degrees, this would be 150 degrees, right? They must add up to 180 degrees because every adjacent angle pair every adjacent angle pair in a parallelogram are same side interior angles created by parallel lines cut by transversals. Now, let's take a look at letter C. Using B above, give an argument for why the measure of angle A must equal the measure of angle C. Parentheses. This argument proves in general that opposite angles in a parallelogram are congruent. All right, so why must A and C be congruent based on what we saw in B? Pause the video now and see if you can figure this out. You could write yourself a little short geometry proof. It could be a paragraph proof. You could just explain it. See what you can think about. All right, well, we know about these supplementary angle pairs, right? So I could certainly say that the measure of angle A plus the measure of angle B is equal to 180 degrees, right, based on B. I could say the measure of angle B plus the measure of angle C is 180 degrees, right, because they're also supplementary pairs, right? I can say this. A plus B must be 180, B plus C must be 180. But if those two are both equal to 180, right, then I could easily say that the measure of angle A plus the measure of angle B is equal to the measure of angle B plus the measure of angle C, right? Because they're both equal to 180, they must be equal to themselves. And then I could just subtract the measure, whoops, the measure of angle B from both sides of this equation. And when I do that, I find the measure of angle A is equal to the measure of angle C. This is very, very similar, in fact, I would say, hesitate to say identical, to how we prove that vertical angles have the same measure, right? And basically it boils down to if two angles are supplementary to the same angle, so both A and B are supplements of angle B, then they have to be equal to each other. They have to be congruent to each other, right? If angle B is 30 degrees, then angle A is 150 degrees and angle C is 150 degrees, right? Because they all have to add up to 180. All right. So it's kind of cool. Parallelograms have this beautiful property, which is that opposite angles have the same measure and any pair of adjacent angles add up to 180 degrees. Okay. Let's take a look at one last idea, which are subcategories of parallelograms. And this is really how we're going to spend the rest of the unit, on subcategories of parallelograms. We will work extensively with parallelograms and their properties in coming lessons. There are subcategories of parallelograms based on additional properties that they possess. In other words, you could have a parallelogram, but then there's something else about that parallelogram that then puts it into an even more narrow category. So let's take a look at the three most important subcategories of parallelograms. Subcategories of parallelograms, parentheses, all will be proved parallelograms in later lessons. Number 1, rectangles are quadrilaterals that have 4 right angles. 2, rhombuses, or rhombi, are quadrilaterals that have 4 sides of equal length. In other words, all sides are congruent. And 3, squares are quadrilaterals that have 4 right angles and 4 congruent sides. Now, you have to just sort of trust me for now that all 3 of these types of figures are themselves parallelograms. But, of course, if you're a parallelogram, you're also a trapezoid, right? So you can kind of see it, how it goes, right? So let's take a look at exercise number 4. For each figure shown below, write down each category of shape that it falls into. Many will have multiple categories. Great. So for instance, this first figure has 4 right angles, and because it's got 4 right angles, it is a rectangle. All right. But because it's a rectangle, that also means it's a parallelogram. But because it's a parallelogram, that also means it's a trapezoid. All right. Now, I could also go on to say, because it's a trapezoid, it also must be a quadrilateral, but all of these are quadrilaterals, so we're not going with that. All right. What I'd like you to do now is pause the video and see if you can write down all the categories that each one of these shapes falls into. All right. Well, in letter B, all I know is that this side's parallel to this one and this side's parallel to that one. Since it's got 2 pairs of parallel sides, it's got to be a parallelogram. But since it has at least one set of parallel sides, it's got to be a trapezoid. Anything that is a parallelogram automatically becomes a trapezoid. Okay? Now, letter C, based on the markings that it's got 4 congruent sides. Because it's got 4 congruent sides, this is what is known as a rhombus. But as soon as something is a rhombus, it's also a parallelogram. And as soon as something is a parallelogram, it's also a trapezoid. So that thing is a rhombus, a parallelogram, and a trapezoid. Now again, you might be bothered by this, but think about biology, right? That's a good place to start. When we talk about an organism in biology, right? That organism has what? The class, genus, species, phylum, order, kingdom, all that stuff, right? It falls into other categories. Human beings fall into the categories of hominids. They fall into the categories of mammals. They fall into the category of animal, right? So there's lots of categories that a human being will fall into, and each one of those categories then fits into a larger, more broader category. Trapezoid so far is the most broad category we have other than convex quadrilateral, right? And that would be kind of the final one. Oh, this is a convex quadrilateral, but all these would be. All right. Oh, letter D. Here we've got a figure that's got 4 right angles, 4 congruent sides, so this is our square. All right, but because it's got 4 right angles, that means it's also a rectangle. Because it's got 4 congruent sides, that means it's a rhombus. Because it's any one of these 3, that means it's a parallelogram. And because it's a parallelogram, that also means it's a trapezoid. The square falls into more categories than any other quadrilateral. It basically falls into every category there is, you know, more or less. Now letter E, here we've got these 2 sides are parallel and these 2 sides are congruent. Well, the only thing that really falls into, for now at least, is the trapezoid category, right? So trapezoids have at least 1 pair of parallel sides, and that's it. Right? That's the only category that one falls into so far. Now letter F, I've got this side congruent to this side and that side congruent to that side. Nothing indicates that any of those sides are parallel to each other, which means that's not even a trapezoid. But that is what is called a kite. And a kite is just defined as a figure that's got 2 pairs of congruent sides that don't overlap. In other words, I got 1 pair that's congruent, and I got another pair that's congruent, and that's it, right? So they don't overlap. Like this one's not congruent to this one, and this one congruent to that one, right? So that's a kite. All right, let's wrap this up. So today we started what will be a long sort of journey through Unit 6 looking at special quadrilaterals, right? The most broad category being trapezoids, figures that have at least 1 pair of parallel sides. Then we got to a slightly less broad category, the parallelogram, a figure that's got 2 pairs of parallel sides. And then we looked at various other ones, you know, such as the square, the rectangle, and the rhombus, right? All of these we're going to spend at least 1 period on because we're going to want to look at the various properties. We're going to want to prove that all those special types of quadrilaterals are in fact parallelograms. And we're going to spend a couple days just looking at parallelograms because they're that important. For now, I just want to thank you for joining me for another geometry lesson by eMath Instruction. My name is Kirk Weiler, and until I see you again, keep thinking and keep solving problems.